Alright, welcome back to this video, and this video will continue our discussion and the introduction for the rigid body dynamics. So, we'll move on to the topic of description of plane motion. Of a rigid body. Right, so we already defined what a rigid body is, and recall that that body is when it undergoes a motion or when the force is applied of it, then the points in itself the distances between the points and then the angles between the points doesn't change. So let's now describe, if this rigid body undergoes a plane motion. So take note of the word plane motion, because there are many types of motion. Okay, let's put it here. Many types of motion for mechanisms. They fall into one of the following cases. Right, so number one, that's the plane motion. Number two, the helical motion. And then the third one is the spherical motions. Alright, so that's why we just focus on the plane motion. Okay, but at least it's also good that it's introduced here that there are still other motions possible for a rigid body. So here, when you say plane motion, for example, we have this body here, rigid body. Right, so this is the center of mass, or mass center. So it's this one. So let's say that this the path of motion Alright, so let's say this is the path of motion. Then what it's just saying is that we can analyze this as a plane. For example, this is the plane, the first plane that we have, and then it's just actually a representative of, this plane represents all the points here. That it's just like all the points here, they move in the same way as the points that lie in these planes. So if we make another plane, right, this one, or here, so the points here, okay, take note, we are in 3 dimensionals, X, Y, and Z. Right, so if this plane moves from this point to another point, then we can just analyze the points, or the point in let's say points in one plane that lie on one plane, and conventionally it's taken the plane, this plane is conventionally taken as the plane that passes through the mass center of the rigid body. Right, so the point is, this plane is just the same as this one, it's just the same as this one, but we'll just consider one plane here, that passes in these mass centers. Okay, so that's what a plane motion is. Okay, so the next thing is there's actually 3 possible motions for a plane motion. And I think we already mentioned this in the previous video. So first we have a translation. So the translation part is just like this. So this is the point 1, and then it translates here. So take note, this one is not rotating as it translates, or we'll just use another one. Okay. Here, right? So let's say this is our rigid body. So it moves. Let's say this is the point 1, and then it moves to point 2. So take note, this one, it translates, but throughout its translation or throughout its motion, it doesn't rotate. So notice that it's still vertical, right? So so that's point 2, and we call this a rectilinear. But it's also possible that we have a curved path. So for a curved path, let's say this is point 1, then this is point 2. So this vertical here, still when it change when it do the motion, it's still vertical here. So that's a curvilinear translation, right? So again, right, so another motion is the rotation. So for rotation, it's actually or rotation about a fixed axis. All right, so I think let's make this dark. Alright, so for this one, it's rotating about a fixed axis. So for example, this is our rigid body, then this will be the point of rotation, or the axis of rotation. Let's see, axis is actually referring to a line. So this is a point of rotation. So you see, so let's say at point 1 is actually vertical, but then at point 2 it's horizontal. So that's what a rotation is. So fixed rotation here. So this is 1, this is 2, and then this is our motion. Alright, so it's also possible, by the way, so this type of motion actually, you can see this in electric motors or the machines connected to engines, pulleys, gears, systems, shafts. So this is their motion. It's a rotation about a fixed axis. It's also possible, okay, so for the third one, it's also possible that it's translating plus rotating. So in this case, we call this as the general plane motion. Right, so for example, this is your point 1. So for example, this. So let's say this is the path. Right, so here at point 1 it's vertical, purely vertical, but then at point 2 it translates plus it rotates. So you have here, that is point 2, and then here let's say it moves like this. So this is 0.3. So it undergoes translation to, translation plus rotation. Right, so in the next topic we will focus first on the rotation about the fixed axis. So we'll try to relate the translation equations that we had in our point masses. It's actually the same here for rigid bodies. So it works the same. So for example, in our translations we had velocity, the acceleration, displacements. So it's just the same here. What's new is the rotation parts. So the rotation parts, it's not that it's actually really new, because there's a resemblance or an analogy between the translation and the rotation. So the units are just different, but essentially they're just the same. So and the next discussion we have, we'll just focus first for the rotation, and then once we build up our skills on the rotation about fixed axis, get used to the units or their variables, then we can move on to the translating and then the rotating aspects, the general plane motions. Right, so let's discuss first the rotation aspects. Okay, so as I've said, that they're just essentially the same, right? So translation, and then this one, the rotation. So let's have a table. Okay, so here I'll try to draw a diagram here, and then this one, the rotation. Right, so these are path. Then this is our motion. No, not motion, the object. Right, so let's say this is point 1. So after some time, it moves here. So we say that the position, right? So the position of point 1 is now different from the position of point 2. So how do we label the position in translation? We just use the symbol S. Then at some reference point, of course, this position is at some reference point. So the unit for the position is, let's say for the SI, just meter, or for the English, use feet. Now, because it changed position, this is what we call as delta S, or displacement. Right, and then the unit of displacement is just the same, meter or feet. And then the rate of change, so how fast does this position changes, that's what we call velocity, right? Delta S over delta T, or you can take the limits and then use the derivative. So delta S over delta T is just meter per second. Then how fast does the velocity changes? We say that's the acceleration. So delta V over delta T, right? And then the unit is meter per second squared. So the same goes true here for the rotational motion. So let's say this is the point 1 that we have, right? So at some angle, there's it's there. That's the position. So for the position, we use the symbol theta. It's about measuring in terms of the angles. So unlike here, it's more linear measurements. So this one is angular measurements. So we refer to this as angular position. And then the unit is in regions. Right, so after some time, it moves. Let's say it changes position to here. So let's say this is 0.2. Alright, so 0.2. Alright, so from 0.1 to 0.2, what's the displacement in terms of this angle? So we write delta theta, or angular displacement. Okay, so the unit's still in radians. Then the rate of change, so how fast is the position is changing, that's what we call the velocity, right, for this translation. But for rotation, the symbol we use is this one, the curly W. I don't know if this is omega, and we refer to that as angular velocity. Okay, so if it's a velocity, then it's a time rate of change of the displacement, so the unit would be radians per second. And then for acceleration, we have this alpha, and we refer to that as angular acceleration. And then the unit is in radians per second squared. All right. Okay, so again, so for translation, this is S. This one is in terms of angle. And then this one, the change in position, which is the displacement, is just the angular displacement. This one is the velocity. This one is the angular velocity. Acceleration, angular accelerations. And then the unit take note is just in radians. So let's just I think let's just focus for now on what a radian is. So a radian is basically another or alternate units for the angular measurements. So radian is, for example, this is your circle. The radian is the angle created by bending the radius. Alright, so what it means is this. So this is your radius basically. So this distance, this length, if you try to plot it here along the curve or along the arc length, then if, let's say this radius is r and then this one is radius, then the theta that's measured by that is the radian. Okay, so please recall that from here is 0, and then here in terms of radians we have pi over 2, and then this one is pi. Alright, so 0, this is 1 pi, and then if it gets back here, then that's 2 pi. So pi over 2 pi halves. So this one would be 3 what's that, 1.5 or 3 halves pi. So in terms of degrees, this is 0 degrees, this is 90 degrees, this is 180, 270 degrees, and then 360 degrees. Right, so I think it's also worthwhile to mention that there are still others units for these angular measurements. So there's also a grades and then mils. So if I remember it correctly, then I think 2 pi is, I don't know, 400 grades. Then for mils, it's like 6,400 mils. Right, so they're just another set of units, but we're not gonna deal with this in our course. So that's the radians. So again, I think it's also necessary to say here that the 2 pi is what we call 1 revolution. So from this point, and then it revolves full circle, then that's what we call a 1 revolution. Right, so basically we say 2 pi is equal to 1 revolution. All right, so next thing, let's just work on the equations. So recall that for our translation, we have this equation. If you remember from the equations of constant accelerations, so a delta t is equal to delta v, and then the 2a delta s is equal to delta v squared, and then another one, delta s is equal to v at 0.1 t plus 1/2 a t squared. Right, so here the mathematics or the calculus is just the same, except that the symbols or the variables that we use. So here we have acceleration. So for the rotation, we just change it to alpha. Delta t is the same, and then delta v. What's delta v? That's delta omega. So it looks really the same. Essentially, they're just the same, except that this one means the linear thing, this one is the angular thing. So for this equation, second equation, we have 2 alpha, and then what's delta s? So that's delta theta is equal to delta omega squared, right? And then this one, so delta theta is equal to omega at 0.1 t plus 1/2 alpha t squared. Right, so take note that these equations for constant accelerations. So for problems or situations where let's say if acceleration is a function of something, so let's say a is a function of t, or is a function of velocity, a is a function of distance, right? Not this one, I think. Let's say this one, the omega. So, oh no, not the omega, the alpha. So alpha is a function of the velocity, or alpha is a function of position. Then we use the main equations, and then we derive it using the calculus. So recall that our main equation here for the translation is v is equal to ds over dt, and then the acceleration is the change of velocity, time rate of change. So here for rotation, so it works the same. So our angular velocity is just the change in angular position, and then this one, the acceleration, angular acceleration, is just change of the time rate of change of the angular velocity, right? And then again, we can relate this one and arrive to this equation here. So if you equate dt is equal to dt, then you will get this one, right? Right, so what's this? ADS equal to VDV. Alright. So that's the angular aspects, and then there's also a topic wherein there's a relationship between the linear side of the rotation and then the angular sides. So we'll discuss it here. Alright, so let's say this is the curve. Let's say it's a circle. So this is the center point. So let's consider this point for now. So this point basically From this center to this point, we call that a radius, right? Or let's just say position vector. So there's a distance here, and then recall that since it's in rotating motion, or rotation about a fixed axis, so this is the axis of rotation. So if it's rotating, then there's going to be some angular velocity here, of course. Now there's a relationship between this angular velocity here to the velocity that's the linear part, or the velocity that's tangent to this path. So recall, in our topic of path coordinates for point masses, we have velocity here that's tangential. So there's a relationship here, and they have found out that the velocity, this one, the linear velocity, is directly proportional to the angular velocity. Okay, so this is not the angular acceleration, this is proportionality symbol. So the velocity is directly proportional to this angular rotation, and then they say that the proportion is actually proportional to the distance r. So how far is this distance? So when we say r, not necessarily mean the radius. In our figure, it so happened that it's the radius, but you can mean actually any position from the center point to the point of location, I mean to the point of interest. So here they say this is the relationship. So V is equal to omega times r. Now the question is, which one goes faster? Alright, so let's say this is the velocity. Let's consider another point here. So let's say there's another point. So which one goes faster? This one, let's say this is point A, and then this is point B. Point A or point B goes faster? Alright, so take note. So let's say they obtain the one revolution in 1 minute, for example. So one revolution in 1 minute. So meaning that all of them, I mean both of them, will reach this point back in 1 minute. So meaning the time is just they're just the same actually, except that the path that this point travels is actually much larger compared to this one. So see, this is the circle of the B, and then this one is the circle of the A, so it's much larger distance. So meaning in order to arrive at the same distance, it has to travel faster. So here we can see that there's going to be a velocity distribution from the point of rotation to the, from the point of rotation to the particular point that you want. Alright, so this is the scalar form, but we can also write that in terms of vector. So we say that the velocity here is equal to the velocity vector is equal to the angular velocity vector cross product to the position vector. Alright, so take note, this is a cross product, so a cross product of two vectors, so meaning that this vector lies in one plane, and then this is the out of plane vector. So if we try to draw it in 3D, Right, so let's say this is the doesn't matter. Let's say this x is y, and then this is z, and then this is the axis of rotation. Okay, so this is the axis of rotation. Alright, so let's say this is the point A that we are trying to consider. So here we say that the velocity vector, so let's say this is the tangential velocity. So we say that it's a cross product of this angular velocity, which is cross product of the position. So that position is, let's say this is our reference point. So this is the position vector here. Right, so this one, the angular velocity, is also a vector. So basically it's just a rotation here. Right, so we say it's a rotation, but it's actually a vector that produces rotation. So we can draw a double dot. Let's just say this is a vector, another vector. Right, so if you can see, these two vectors are in plane to each other. So if you do the cross product, you'll get this one. So I think this is the illustration for this cross product thing. I think so. It's also true for the acceleration. So let's just put it here. So they also say that acceleration is also the same. So it's directly proportional to the radius. So this one is the same. But take note. So recall that, for example, this is our object here, and then this is our point of rotation. And then recall that we have two aspects for this acceleration. We have the angular, no, not the angular, the normal acceleration. So that's the acceleration vector that's pointing towards this point of rotation, or the center of rotation. And then we have this tangential. Okay, so here the tangential part, they say that it's also directly proportional to the radius, and the normal acceleration is, recall that our equation for that, for the normal acceleration, is v squared over r. But then what is v? So v is just omega times r squared, so all over r. So you get this one, omega r. Alright, so this is the acceleration component, this is the velocity component. Okay, so we can also write this. Okay, so we'll use another sheet of paper. We'll just do it here. So if we write this in terms of vectors, then we'll get this one. So the acceleration vector in the tangential coordinate is just equal to, okay, the cross product of r. Let's box this one. So here the normal component of the acceleration, it's actually the cross product of r, or let's just do it here. All right, let's just do it here. So this one times another cross product of 4, right? So please, the position of these cross products are important, so try not to mix them. So this one can be simplified into w squared r. So this is an, right? So this is the acceleration vector, and the normal component, and then this one is just simply the product of a scalar version of the angular velocity squared times the position vector. Okay, so you see here, if we all draw another one, so let's say this is the acceleration vector here. So right, so let's say this is the r position, and then this is the tangential. Oops, it's this one. And then we have another component here, the normal component. So the if you can see this one, the normal component of the acceleration is just the opposite. The direction is just opposite to the position vector here. So that's why the equation is negative here, right? So the direction is opposite, and then the magnitude. So think of this is just a scalar times a vector, right? So it just changes the magnitude of this vector here. All right. So in the next video, we'll do sample problems for the rotation aspects, and then after that we're gonna extend some topics on the speed ratio, because you're gonna encounter that in your subject or in your course on machine design, I think. So you'll deal with those things. All right, so I hope you learned a lot here, and then see you on the next video.